questions and answers there.
Should we go around the room? Maybe we have a small enough group, we might be able to do introductions real quick. Yeah? Yeah. Well, first, I'm Jake. I'm the fellow for this organization. It's weird speaking in a microphone, but I'm a second-year PhD student at Indiana University. I'm a sedimentologist. So yeah, and I support the EnviroSensing cluster.
Hi, my name is James Gallagher. I'm actually the president of OpenDAP. But I'm here as a person who also does some work with programming embedded devices and builds embedded devices. And my wife is a field ecologist who's also part of this cluster but could not attend this meeting now. So anyways, we're interested in all these things and in building sensor systems that are really inexpensive and can be contributed to meaningfully by undergraduates.
Hi, I'm Sven. I'm with the Kellogg Biological Station, LTR, and I'm data manager there. I collect to dabble with stuff like that. So.
Yeah, I'm John Porter. I do the information management at the Virginia Coast Reserve, LTER, but I've also, we have a lot of sort of wireless sensor systems that we sort of deploy across the landscape, because when it takes 45 minutes in a boat to get to any place, that's of real value. And but I've been interested most recently in trying to get to places that don't have the possibility of the sort of infrastructure we have at our other sites, which is to say places where you can put large arrays of solar panels and those sorts of things. So I've been looking more at sort of devices that can, live off their own batteries for long periods of time and that sort of thing. Anyway, I have tons to learn.
I'm Adam Sapp. I am the information manager for the GCE LTR, and we have a similar coastal environment as John there, and a lot of remote sensors and that kind of thing. We've got a few people that have a pretty good handle on how to do this stuff, and then a lot of people that are very resistant to it, and I'm kind of in the middle. I don't know that much about it, so I'm looking to learn, and, so I can help push this kind of stuff forward at my site.
I'm Mike Daniels. Let's see, formerly I worked at the National Center for Atmospheric Research in the Earth Observing Lab. So we had in situ sensors, aircraft sensors, remote sensing sensors, radars, and profilers. And so I had some experience with observational data. I became the PI of a project called CORDS that's funded by NSF to take time series data of all kinds and ingest it easily with web services. And then I retired from full-time work in 2019, and I was looking for fun projects, and this just hit me. And it really applies into time series data. But we're working with community colleges, and I have these 3 kits that you put together, and then all of a sudden data appears into a server back in Boulder, and make it very simple. But that's what I'm really interested in, engaging with this new technology and the accessibility barrier that's been lowered because of it. Oh, I'm sorry.
Sorry. I snuck in. Hi, so I guess we're doing introductions. I'm Steve Young, a longtime Environmental Protection Agency employee, retired. And I'm interested in the whole sensing thing as well as a ton of other stuff. I just stood up my purple air sensor, and so it's in my backyard reporting data. You can see it live. So I feel like I actually have skin in the game now. But I'm interested in use cases like where I live, our small streams are incredibly flashy. So with these enhanced precipitation events that we're all seeing, these streams flash even like a 1/4 inch of rain. One stream will flash. There's so much impervious surface. So my fantasy has been to do a couple of stream gauges that would do real-time monitoring of these very small streams where I'd be able to see what's going on and actually begin to characterize the flashiness, and have some data that I could show to decision makers and say, what the heck are we doing? We're still creating more impervious surface, right? And so anyway, that's a particular interest of mine. Thanks.
Hello, everybody. My name is Matthias Search. I'm with the Forest Ecosystem Monitoring Cooperative. On a personal level, I'm interested in monitoring wildlife, hopefully in a more inintrusive, hands-off kind of way. So this interests me, and I'm here to absorb whatever you guys have to say.
Hi, I have an interesting hat on. That's why I'm here. So Shelley Stahl at the American Geophysical Union, and I'm actually co-chairing a Birds of a Feather session in RDA coming up this fall on data coming from instruments and being as fair as possible. Very popular, and I am a duck out of water trying to make this happen. So I came here to try to find fellow feathers, so I'm learning from you.
Hi everyone, I'm another community fellow here. I'm part of the Community Resilience Cluster, but I studied electrical and computer engineering, so I used to play around with a lot of sensors. And I also worked in air quality, so I know a lot about air quality sensors, so I'm excited to be here and nerd out about sensors once again. It's been a long time.
Yeah, this is great. I got on my center just the other day about purple air. And, we're getting hammered up here. When it doesn't rain, we can't see the sun because the forest fire is from Canada. And in the GS, we don't do much monitoring like this, right? We have prescriptive monitoring and we also have threshold monitoring, but they cost a lot. And I think John's point about like where can I hang this stuff, and the cost to monitor for the GS keeps going up and up and up with the need for a station, like a full-blown station in every spot. But we don't need that, right? We're seeing this change. It's a paradigm shift. Like every gauge house doesn't necessarily need a data collection platform, right? It just needs an ability to transmit to a gateway, right? And so we start to throw these terms in, gateways and nodes, and they sound different from maybe even like 5 or 6 years ago. And sometimes they're intimidating, but really what we're looking at doing is relieving some of the stress with respect to the need for resources from a monitoring network. A cool part, somebody was speaking to somebody at lunch about why EnviroSense and Cluster, why do I like it? But it focuses on in-situ monitoring, and that it really truly grounds all other monitoring, right? If you have satellite data coming in, you need ground truth. Right? If you have drones flying over a space, you need ground truth, whether that's a GPS point or an observation, a like observation of the same parameter of monitoring. So an ability to distribute low cost, not cheap, low cost sensors is fantastic, and it's going to drive and promote monitoring. One of the components to this style of monitoring that impressed me was these sensors are designed out of the box to present you with numerous forms of data. Not only do you get your temperature data, right, it's 25C or it's 50F, but you get a relative signal strength indicator with each observation. You get a signal to noise ratio with each observation. So you can start to pull in these other operational data, if you will, to look at the quality of your measurement and what might be going on at your site, right? If you have a relative signal strength of, I'm just going to throw a number, 70, and now all of a sudden that same value is up to 90. Well, what's going on, right? Has an obstruction been placed in between your sensor and where it's trying to transmit? Is it a heavy, humid day? Does rain impact these sensors? So just quickly, and we'll get off the title slide and jump into things, but like this is, it's a spectrum of a session. Teach it to me like I'm a 5, to let's dig into the most complex, nerd out components of this. And for me, I'm in the middle. I've had so many great people, Daniel Fuca, Scotty Strachan, right? All members of the cluster, Martha, James, Gallagher. These folks really helped me along in this section. Wireless monitoring it's new to the survey, it's new to me. So that's been a great community, and they've helped me. They taught me like I was 5, so I'm in the middle. I'm 15 now, right? So, but yeah, so like if we say words, if we use phrases, and this is a great opportunity to be like, yeah, what is that? What do you even mean by that? We have folks with neat little toys in here, and this is great. Like this is a really cool pivot. So what I think we can do is we'll just have a quick open question session, and then we'll just put people in the hot seat, right? Like maybe Mike, if you don't mind, you could take us out and show us. We'll do a show and tell bit. Like what did you bring? Because like this is for the, oh my gosh, I just brought up some political ad. But like so much of it on the GS side is really explained in this slide, right? We have teach it to me like I'm 5 Joe, and we have an iPhone that plays through 1955 keyboard, right? No wires, right? No wires. There's radio frequency modulation to hack into the station on the radio that's right there locally, and you don't have to rewire your dashboard, right? So here we use an older car, new technologies coming in, and show an example of how they can integrate without having to rework the whole thing again, right? So all the questions between how do you do points, right? What the heck is a point in an engine, right? Now we have fuel injection, but how do you measure the gaps in the spaces that keep the old things running? And can you do that and monitor it now with just a small upgrade device, right? There's not much on the console. You're going this fast. Your water temperature might be this hot. You go into a Tesla now and you're getting cell charges from individual batteries. You're getting power reclamation for each of the wheels. These are all done through sensors, right? So automobiles also rely on this technology, both wired and unwired, to deliver it. So yeah, so right there, we'll just give us your best question, or the one that's kind of bugging you. Let me think of one that I had. Yeah, so there's a lot. How do I get this data so that I can see it, right? That's the problem that the survey was trying to face when it looked into whether GoRock or these wireless technologies, ZigBee, can play into the mix. And what we learned early is that our infrastructure isn't set up. The existing infrastructure for the survey and how it monitors the data plan wasn't set up to inject these nodes, right? These small sites that can go out and basically just report out and wake up and send out a signal maybe over 2 years. Last 2 years, a sensor lasting 10 years is unheard of in the GS. Maybe sometimes we're out there every 4 weeks to check on it. So the platform, the stack, if you will, the data stack that comes and allows comes into play and allows the data to show up on the Things Network or the USGS Water Now stuff requires a change in infrastructure. So what we recognized was a closed-off database really wasn't going to work unless we set up our own servers. So you kind of see this branch where you can do everything by yourself and in private if you build it and dedicate your resources to it, or you can tap into this other vein that's already developed, like Things Network, for example, where you can supply your gateways that communicate between the sensors and the Things Network platform and get your data. So for me, answering that question was the answer to that question, how do I see my data, with 2 parts. Right? You need to build some infrastructure, and you need to establish connections to servers, right? Like the LoRaWAN server. Who is going to decode this data? Right? So like, you get your observation, in a human, you look at it, you don't know what it is, right? It's in hexadecimal, so it's just form. That data flies across the airwaves, gets to something like Things Network, and it's decoded. So now you look at that same observation and gives you the temperature and place of which it is. So for me, it was how do we get the things, these little sensors, to speak with existing networks? And in short, you have to build some stuff, but then you also have to change your approach and embrace some of the stuff that's already established out. Things that I'm gonna start picking on people, but I don't want to pick on James because he's too easy. Would you mind? Yeah. Sure.
Asking questions, telling stories.
Either way, what helps out just a community session.
Yeah. So yeah, I think I mean this was. I guess one of the questions I have would be a lot of our PIs are in. There used to be robust sensor systems like Campbell loggers or something see some of this low-cost stuff that's disposable and not dependable, and so we kind of struggle to sell them on that point. That, you know, these things can't work and do something valuable, even if they're not going to last 100 years. Like, I don't know how. Oh, why did you speak to that?
Shall I use the microphone? Yeah, so one of the things that we were really interested in is instrumenting the alpine areas. So that's above the tree line. So you're talking about a really harsh environment. You're talking about an environment where things like large solar arrays, not part of the question. So we wanted to build very, very low power sensor systems that could operate at extremely low power budget. And we started looking at the various commercial options, which we certainly have access to, like the meter loggers and so on. And one of our questions was, okay, can we equal their accuracy? Can we equal their precision? Can we equal something that's as robust as them? So we have done some deployments where we placed sensors in those environments and left them there for a year, and they functioned. They recorded data during that entire period. And then we were able to also install some of those same sensors in the same places where we had the more expensive commercial equipment, and then compare the things they measured. And we found that, number one, first of all, the things that we deployed in the alpine environment, they survived. They functioned for the entire period of deployment. And they were configured such that they used more than their extremely low power budget mode of operation. So we were sort of stress testing them. And then similarly, we found that the temperature data that our system, our little sensors, some of these ones right here, in fact, collected, matched up with the information that the meter logger was measuring to an extremely high degree. In fact, when you overlaid them on the same plot, you really couldn't tell the difference at all. So in that sense, yes, and yes, we can reproduce the dependability, and we can also reproduce the scientific sort of veracity of the information, even using sensors like these things, these little silver duties, which are a couple bucks each. If you get them from a Chinese distributor, they're $30 if you get them from Adafruit. These things are completely bespoke. The case is commercially made, but the circuit board is one that we designed and had made for us. This blue one is actually from a Belgium manufacturer. These green ones, they come from China. You can't do this with USGS money, but I can do it with our own money. And so yes, so you can equal it. And you're right, you will have an acceptance criteria that you have to cross. But you should be able to cross it.
Which sensors, like what kind of sensors were you testing? Temperature, moisture?
Yeah, well, so temperature and relative humidity is actually what these boxes measure. So soil moisture, it turns out, is really complicated. It's a really tough nut to crack because a lot of soil moisture has to do with like the surface area of the particles of the soil. And so a typical way is to measure with capacitance or other techniques.
Using the SDI-12 sensors and just throwing the logger out.
Yeah, right, exactly. So one of the things with, it's kind of, well, we could be going down a rabbit hole here. Should we go down the rabbit hole? So a thing about SDI-12, the 12 stands for 12 volts. It's 12 volts. But yeah, so it takes a lot of power. But most modern SDI-12 sensors will actually run off a 5-volt system and maybe even a 3.3 volt system. So like we have experimented with that a little bit, but there hasn't really been a whole lot of motivation for us because we can get these other sensors relatively inexpensively. Anyways, I should hand the microphone to somebody else.
Yeah. Get my steps in.
Yeah, I was just going to add to what Steve said. So yeah, that's exactly what we're doing. We're taking these very cheap sensor systems and comparing them with established systems that cost thousands and thousands of dollars and finding the same thing that Steve found is maybe there's an offset, and once the offset is adjusted, then everything it works. So we did notice that. I think there's also been some work in providing a certified station, via the WMO, and that might be, maybe it's not going to be the classification of a big mesonet network, not have that quite that level of quality, but there's another level of quality that could be certified. So I know this 3D Pause, it's a weather station with 3D printed parts, is pursuing that. So that's another thing happening in that space.
So there's some terminology, right? SDI 12, serial data interface, 12 volt, 1200 baud. Back to your Campbell Scientific question, right? We sit down in front of this blinking screen when we get in front of a Campbell. There's nothing more intimidating than the programming interface of the Campbell Scientific logger. For me, I mean, it's like, it's just a blinking cursor, and you're left with like, I gotta write this, right? It's got some language, CR basic, derivative of CR, of C, and you're writing those codes, right? You're calling on a library, you're calling back to invoke an SDI 12 library function to talk to the instruments, and they're very power hungry and very limited, right? We spoke a bit about the extra data. When you send out a command in SDI 12, it's M, right? You send this measure command, M bang, and you get one value back, right? It takes 30 seconds or 90 seconds, and you get your parameter. You don't know anything about that parameter. You don't even know how it was made, manufacturer derived, boom, there it is. So this is how this is that crack or fissure, if you will, that I'm using to bring others into this realm, is that if your sensors don't have to be these perfect benchmark SDI 12, $4,000 to $12,000 sensors, if stability is there, right? If out of these new sensors you can bring in things like variability of the measurement, now you're even more powerful than that one sensor, right? Because now you're getting a measure of variability. So that the question of, well, I have 10 years of time series, will this next observation mesh into that, right? With statistics, you can bridge that gap, right? So you start to build another time series and you start to do these significant differences. The weather folks, man, they have the national deposition sites and such, decades of records that they are now basically bouncing off against to show, is the variability in the time series I have now consistent with that in the past? So the ability of these new sensors to provide additional parameters more quickly, lower power, more distributed, right? Campbell Scientific, they give the government a little bit of a break when you buy them, not much, but when I moved to a farm, I thought, oh man, I'm gonna put up my Campbell, I'm gonna have my soil set, and then it was like $8 or $9 grand to get a Campbell logger, and I was like, man, Joe homeowner can't do this. I gotta go find one that's not working in the GS and get it working. But to the point, right? The gateways we have, I saw one, packet forwarding devices, $100, $200, multi-tech IP67, which is just a measure of how robust it is, right? It can stand up to rain, it can stand up to wind, it can stand up to moisture. Multi-tech is the manufacturer, and they make a low-rod gateway. Even that, it's like the moving truck of LoRaWAN, and you just pack it up and go across the country. In that sense, it can push a lot of data. That's coming in at $2 grand, right? So here is this kind of situation where the community of data collection platforms, DCPs, Hydromat, Campbell Scientifics, they've went a direction, and it's gotten quite costly. We see these things, LoRaWAN, Zigbee, Cell, Wi-Fi. These are positive disruptors to that environment, and so that's one of the angles that I'm working, is that these data can, when you can program them, you can get more from them and show how they relate. Go ahead.
Is one of the things also is, if you think of the old days with Campbell data loggers, well, it used to be you hooked up a ton of wires to a Campbell data logger. Why did you hook up a ton of wires? Because each sensor was an analog sensor, and what you were paying for in a Campbell data logger was the ability to accurately read what voltage or what current was coming back from that sensor. These days, most of the sensors I'm using are digital sensors. They don't send back a voltage, they send back a signal. Instead of having 25 wires connected up to different analog to serial or analog to digital ports, I've got 3 wires, and all the devices hook up to those same 3 wires. Same thing with in terms of the little circuit boards here. There are protocols that basically you hook up 10 sensors to the same place. And why can you do that? Because they're digital sensors and each one sends an ID. It says, I'm sensor number 75. And so it can interpret it there. So you're not, so you don't need that super A to D sort of conversion type of thing. Now, there's still some things that are really expensive to measure just because getting the measurement in the first place is very hard. If you're trying to measure, picovolts, well, yeah, you've got a problem. But the other thing also is the separation between the sensor and the logger, or the logger function, because in some cases there isn't what we would conventionally think of as a logger. This is a turnkey low-Ra unit. You take this unit, you put a little jumper on it to turn it on so that it's powered up. You put the screws back in, you type a number or scan the QR code off it, you stick that in, and the data starts coming in. Now, the thing is that this is not storing any data at all. It gets a measurement, it sends the measurement, it moves on to the next measurement. So you do need to have a reliable gateway or someplace, because you could basically, if your gateway goes down, all your sensors just went down, okay? Now, because this is a turnkey one, I can't do sort of a lot inside it and things like that. By the way, this is a little LiDAR sensor. It measures distances. That's what that does. But I've got ones that measure temperature and things like that. But if you were actually sort of fabricating your own things, then I'm nowhere near your level. I do not design my own boards and have them built for me. This is stuff all coming, over the internet. I purchased this. But the thing is that in this particular case here, I threw in an SD card. So it actually is logging the stuff locally, but then transmitting it. My purpose here is this is for a rain station that's a 45-minute drive from our lab. I would just as soon not have to drive 45 minutes to see whether it's clogged or not. I'd like to get the data back. But if all sorts of bad things happen and the data doesn't get transmitted back, I've got that little SD card that has even higher resolution data than I had originally. So it doesn't have to be sort of one or the other. But the big change has been that business of separating the sensor from the logger. And before we had wires, now we have wireless. That's the thing, is this sensor's just reporting back that way. But the thing is, I'm willing to put this out in the middle of a lagoon to measure temperature. Well, this isn't a temperature one, but to measure temperatures, to measure things out in the middle of a lagoon. But I am not at all confident that I'm going to get it back. This was about $60. It's not that dissimilar from the little hobo data loggers the little onset computer loggers that we've been using. But the advantage is I don't have to go out to the middle of the bay to collect my data. It just comes back. So, and I don't have to worry about a $1,000 Campbell data logger sitting out in the middle of a bay somewhere waiting to get washed away. Not that I want this to get washed away. But those are sort of in terms of thinking about it. Those are some of the big differences. Is you have to. It is a different thing than I'm going to set up a data logger and that data logger is going to be collecting all the data right on site. It really is more in terms of sensors as individual things, and you might have 15 different sensors all at one place measuring all of the things that you might have measured with a Campbell data logger. But it's also true that you can say, okay, well, I'd like to put one temperature sensor here, another one 200 meters that way, and I'd like to have a rain gauge over here, and I'd like to have that over there. So all of a sudden now you can, the range on a lot of this low power, low ROS stuff is certainly a kilometer, and I've actually gotten it up to 20 kilometers. Mind you, that was very good antenna to very good antenna, not going through a lot of trees and things like that. But usually, 16 kilometers, I think, is sort of what you think of as an optimistic range for a low ROS sensor there. But they're, and like I say, this is a turnkey one. If you can put a jumper on, undo screws, put a jumper on, and type numbers in, you can have this. So a station can be a whole lot bigger if it's wireless.
Yeah, that's a great point. You want Jeff?
I was just wondering, if you just look at temperature sensors, there's probably a few hundred chips sensors out there. Any sense on what's good, or are they all the same, or? I mean, I don't have any idea.
Well, so in the automotive industry, there's a lot of need for things like relative humidity, temperature, and pressure. And so there's a number of good sensors that have come out of that realm, and they're typically available in this kind of maker culture, and they're usually $2 to $3 each. They're surface mount components, so they're extremely small. I'd like to show you one, but it's in, like, one of them is inside this gizmo here. I'll take off the metal housing in a moment, but you'll see that it's about the size, well, it's half the size of my pinky nail, the actual sensor. And that is completely integrated. It not only senses temperature, but it does exactly what John was saying. It uses the I2C bus, so it's a 3-wire bus. And it's sending digital information. It's saying, I am sensor such and such a number, and these are the values that I'm reporting. And so that goes right into a computer. So the value of that can't be understated, because what that means is that there's not a long path for an analog signal to travel. It's exceptionally short, like fractions of a millimeter. So there is no need to compensate for the length of analog signal travel. And these are very inexpensive because the automotive market is so large. There's so much demand for these types of sensors that there are very many made. And they're surface mount components, so they have this extremely small footprint.
So you don't test each different, when you buy different sensors?
We do test. Actually, we have tested many of them to see, and they do all come up similar. Yeah, and these ones, they're $30 from Adafruit. They're cheaper from other places, but they're robust. Some of these boxes, I forget which ones, but one of these boxes was buried in the Alpine for over a year and functioned, and got dug up by me. So this stuff is robust and produced good results.
The one thing I will say, though, Sven, is that resolution sometimes matters. Because a lot of these things, they might be giving you readings of a quarter of a degree jumps. If you are needing to distinguish down to hundredths of a degree or tenths of a degree, then you may have to pay for a higher price sensor, but it still may hook up in the same way. But it's so a lot of times what people do is you will look both. There's a inverse between the range of the sensor. You only have so many bits to say what the value of something is. And if you're covering a big range, then each one of those little bits has to cover a bigger chunk. If you're doing a smaller range, then it can be more precise. So there's some balances out there. But that being said, I know of very few measurements that I do where I care about a quarter of a degree Celsius. Especially since when you average it averages out pretty well.
Okay, so I've been involved in time series data for a long time, right? From these big platforms. And I'm more new to the IoT stuff, maybe 5 years or something like that. But one thing I've noticed is the plethora of sensors, of manufacturers, of cases, and I think, and you know, I'm looking at it from the standpoint of taking these to a community college, getting them to the instructors and say, here's how you build a weather station. You need these components, you know, configure your software like this, and then you're good to go. But the stuff changes so dang fast, and you next thing you know, this sensor, or sorry, this microcontroller is now replaced by that one. And so almost like when the car industry first came out, there are all these different vendors, and then there's just a few after some period of time. So I wonder, you know, we're in this state where there's just so many, and I mean, there's some standards, you know, staples, I'd say like a BME 680, measures temperature, pressure, humidity, and then gas, which has changed. But I think that's one thing that would help, is to try to, you know, go to some common core of things that we can package, because it makes the complexity so much harder. Now you go to Arduino, you're going to program this microcontroller. Well, which board do you have? Well, it's this board, but which version? You know, it just goes on and on and on, and it makes it very difficult, especially for people that haven't ever done it before. And so I think that's one area that I've noticed. It's just amazing and mind-boggling how much stuff is out there. It can keep you always looking at the next shiny object, and sometimes you don't want to do that in the education setting. So.
I'm going to throw a plug in for the cluster here. Like this come to the clusters meetings and ask these questions. Right? It's such a powerful statement. Like how fast those instruments are changing, and like manufacturers being purchased by other manufacturers. The big manufacturers got their eyes on what's being done in the universities, what's coming out, what's being put together at small labs and small companies, and they're actually starting to buy those to make them larger. The other thing, Mike, I wonder if you would take us out for the demo. And while you're doing that, I'll run my mouth over the phone and take us out. Well, you said you had some sensors?
Three kits.
Yeah. Okay. Thank you. Oh, would you mind getting them going? Sure. And so one of the important things is Mike is going to put together a demo here. Is like we can merge these things together too. Like if I have a Campbell logger, and if I have a Campbell logger, right, and I want to get an IoT sensor to it, how do I bring this into my existing network? Right, there are stacks or hacks, if you will.
Just plug this guy in. Yeah, sorry, HDMI.
I think, would it be easy enough to, I guess we can screw it.
Sorry about that.
Oh, you're a board member. Yeah, let's definitely do it.
One of the other things that I wanted to cover quickly as we get set up, there's like 3 controls, right? There's power, there's distance, and there's line of sight. These are basically the 3 things that are going to trip you up in wireless. Right? Power, the more power you have, the more data you send. Distance, right? The further you are from something, the longer it takes, the more disruption in that packet that may occur. That's power. And then line of sight. This is where I get to be bringing my Northeast reference with hockey, right?
Come on, baby.
Shooting at
There you
the
go.
net, no one gets clear line of sight, right? Nothing's going to disrupt you. Start to put people in the middle, now you have a disrupted line of sight. Put a goalie in there, and you probably have to lock line of sight, right? So you have these different steps that may or may not rule out reception.
Okay. Okay, so I've been working on with Dan Fuka. I'm just going to go quickly through. So you should know what IoT is by now. It's basically sensors everywhere. It's in your house. It's in your car. It's the cost of sensors is so cheap that there are sensors all over the place. We had a workshop in Hawaii in 2018 where we had a bunch of sensors. We had a bunch of early career folks, and we in a short 1-week workshop we deployed 8 sensor systems in Hawaii. And people like me were soldering things together. So if I can do it, anybody can, kind of thing. So let's see where I want to go with this. Yeah, the other thing that we've been really involved in is 3D printing of both especially the housings and then the radiation shields. Because if you're measuring temperature, you have to worry about the sun radiating on the temperature shield. But then we just print these with a 3D printer, and so it's easy to replace, easy to redesign. So this is what the weather station itself looks like. These are all 3D printed parts with some PVC that you just go to your hardware store to buy, right? So that's the kind of cool stuff that's happening there. And And then, as James has done, that you can partner with some of these organizations to build your own board. In the case of Dan Fuka, yeah, it's going to be flaky. I'll just do this. Let's try if that works. Yeah. So in the case of Dan Fuka's group at USDA, they partnered with Spark Fund to actually design a board that did everything that they wanted to do. Other times you can just buy stuff off the shelf from adafruit.com, as was mentioned before, or other places like Mauser and such. This is the Chords platform that we developed under NSF funding. You can see it at chordsrt.com. It's not commercial in any way, by the way. I don't know why we picked that domain name instead of .org, because it's really funded through NSF software. But basically, you use, it can run in the cloud, and then it can, so you can get a cheap AWS instance, put it in the cloud as in a container, and then start sending your instrument data to it. So it's containerized, and basically it just has a URL interface, a web services interface. And so now, and since the IoT world is really MQTT, that's the protocol that world uses, there's a connection from Chords to MQTT to basically transmit or translate what's MQTT stuff into Chords web services. And so we have this notion of data being born sensors and their data being born connected. Not just a sensor just appearing all of a sudden, but actually being connected to something. And so Chord's vision was to have some standardization for these measurements, especially in terms of things like controlled vocabularies and putting things in formats that are common. So that was the whole purpose. It's sort of a geosciences IoT package. So here's our working demo. So yeah, you basically take the microcontroller, you connect it with a bus that we were talking about before to the sensor, and then you power that microcontroller through the battery that you have, and then that other device is just a hotspot. It's a Wi-Fi hotspot. So the components, the microcontroller is $8. Some of these connectors are $5, $2 for the cable. The sensor itself that measures temperature, pressure, humidity, and VOC is a $19 sensor. The Wi-Fi hotspot was the Wi-Fi card, the Wi-Fi service is $30. The hotspot itself is $37, and the battery is $39. So the battery and the solar panels and those kind of things are way more expensive than the actual sensors. So what we're going to do is connect these up. Let's see if I have Okay, so the first thing you have to do is take the Wi-Fi hotspot and then plug it into your battery, and then make sure your battery's on. You got that going? Okay, so now this takes a while, so we have to. So it's going to get a signal from the cellular network, and then it's going to create its own little Wi-Fi hotspot. And so what we're waiting for is a blue solid light on your Wi-Fi hotspot.
Oh, there we go. 1 minute old.
Yeah. Okay. Getting data. That's always good. So everybody can go to this URL right here, SISL-chords, .cloud.ucar.edu on your phone or wherever. It's a responsive web application. And then the number written on your microcontroller corresponds to code, the code and then that number. So if you have microcontroller number 1, you'll be code 1. You'll see that we have code 2, code 4, and code 1 in this room, and they're sending data right now. So if you want to breathe on your sensor, it's sampling about every minute. So it's not a real frequent sampling, but after we hold it,
And every instrument comes with just the tiniest amount of smoke. Yes. It's super important to know that. Yes. And you can't refill it. So if you ever touch it and it goes smoke.
Yeah, we refer to this as a bad smell. The big thing about it is there are two kinds of people. There are those who have hooked the wires up backwards and made them
permanent burnout and those who will. So the point is, so we're going to reflect the fact that at some point in your future, there will be a problem, maybe a little bit of light, a puff of smoke, and a bad smell, and it's down to get another. That's it. Yeah, at least two. And that's okay. That's all right. That's fine. We're not getting $2,000 one, well, the temperature, it's better than what we get on minor conversion. You got the one half of 4.5, one is now. So, the thing is, you have this side, it's someone that's three times they'll hold into it, that's expecting. It's now essentially got a lightning bolt goes through it and burn out the part. And then
All right, so just quickly, we'll give you 5 minutes of your life back, but one of the things that we would like to do as the environmental sensing cluster, and if Daniel was here, he would be pushing this, because this is really his idea, where his session was just kind of helping him out, because he got stuff in our one. The next couple of sessions in the environmental sensing cluster, we're going to introduce Daniel to the board and maybe start to think about like a session build, if you will. So keep in touch with us. Jake's got 40 boxes or 40 boards in a box in his room right now, and the idea is to look at. So there's been talk about kind of coming together on a sensor, or so maybe there's something there. So maybe keep in touch with the cluster. We're old, right? And Jake's not helping us much out with Slack here, Jake. So on the Slack channel, I get so intimidated when I think it's like, so many words. But I communicate over Slack, so you can hit us up there. Megan does a fantastic job of policing us and saying, hey, get to your Slack channel, I guess, to their company. But yeah, so communicate through that, communicate through decent emails. Check us out, Enviro Sensing, like I said, using like a 5 or hit me with all the details. And this is pretty cool, right? This is what we're after, crowdsourcing, low cost. So much of what we talked about today is what Purple Air is, right? They built there, and then what Mike's on the way to doing with the Android community. You have a platform, you keep it simple, and you drive it. You just keep driving it internationally, right? Into the communities, build a data cache, build knowledge. Don't be afraid to ask questions. The first question I asked that I got laughed at off the conference call was about imagery. I didn't know anything, should have done my homework, but I didn't. I ran my mouth and said, how are we going to get imagery over the lower? Right? So there's protocol, it's just a protocol. And it was just silence, and then there was a little bit of laughter. I was like, oh god, whatever. But it's just like, I was thinking massive data, like picture, and this other person's got their hand out waiting for a mark. So it's like, there's some things that just aren't a thing. Our sensing cluster is a great place to ask those questions, not to laugh at. So just to sell the cluster a little bit more, yeah, look us up, connect with us, ask questions. It doesn't have to be through our session. Folks like James, it's just so awesome. Mike and others that share, John, that shared. It's like it's just a really great information exchange. Go ahead.
I'm just curious. Is the environmental sensing cluster like people, like tech sensor people that got interested in environmental sensing, or environmentalists who got interested in sensing?
I'd say both, probably.
It's really beautiful, but so Scott Strachan, he's not here today, but I kind of have him as the lead chair of environmental sensing with the cluster for a while. He did a really great job of balancing that. Right? A lot of I put a GS, just use the term hydrologist, but researchers, they know the question they have to answer, but they don't know the sensors and the techniques to use. Right. And then we really minds like James, we can build the sensors. He's like, hey, that's a great idea, but I want to build it. So you bring these groups together. And James makes money from the researchers who buy his instruments, and then they make money because they've got them in their data. So, yeah, it's a really nice blend. And I think this is a micro representation of that group.
Cool. All right.
We do it.
I think we're good. I think we're good to go. Officially can stop recording.